Okay, I'll start recording. Can people hear me? Good. Any questions about last class? So one thing I'm going to do is to cover some of the material from last class in the first 10 minutes because the video does not exist. I forgot to tape, so that material will at least be recorded. You will have some material to follow it along. So let me open my notes. So as I do that, I can tell you a little bit more about the midterm. So there are six papers that you have to pick from, and around 57 of you have responded. Please, the others who haven't responded, please try to do that by today, 2 p.m. So then I can assign you in teams. You will, if you put in your response, then I can promise that you will be in either, you will get either a paper that was your first choice. You will be in a team where everyone had the common first choice or second choice. Then it's up to you as a team to figure out which paper to pick. You can have a discussion. You can have a fight amongst yourself. Like, no, I like this paper more. And you have to convince your teammates because you might have a paper which is your second choice and you might want to go for it. So have a discussion with your teammate. You will know who they are. Schedule a Zoom meeting or whatever. Talk to each other and figure out which paper do you actually want to work with. As a team, if you decide that both of the papers that you picked are actually super crap and you want to go to another paper, that's also fine. You're not committed to taking one of the papers. I would be very surprised if you do that. You pick up papers for a reason. So if you actually end up going to some other paper, that would be surprising, but you are welcome to do that. But you have to make decision as a team. After that, there will be a few things that you will have to do in your report. I will be expecting some specific outputs from you regarding a paper, and I will tell you what exactly they are. Nothing will be vague. 5 people in each group. So one group might have 4 people because the class has 99 students. Maybe we can put Connor in one of the groups. Let's not bother Connor more. Or maybe I can join one of the groups. That will be fun. So and you will be making 5 different reports, but one common presentation. Pakora, you don't want Pakora. He will he will eat your papers. It's his birthday on 3rd of November, by the way. It's his second birthday. So, and then you will make a presentation. Only one of you has to record a presentation. Not all 5 of you have to record a presentation. If for whatever reason you believe that you really want 2 presentations for your team, you are welcome to do that. I will be grading you on the basis of the best presentation of 2. If you believe you want to put in 5 different presentations, that's also fine. I will make a Google Drive where there will be different team folders and you upload your presentation. But one presentation is completely fine. Everyone should have an input. And I imagine not all 5 people in the team will have the same recording capacities or good quality software to record the video or audio or things like that. So you don't need video; it's just a presentation, and it's a good something to practice. And you will have 3 weeks to do that. It should be fun. This homework. Last time I gave this as a homework, and it was a lot of fun. That's what the students told me in the anonymous feedback at the end of the semester. So hopefully you will enjoy it this time too. And you will have to work. You will have you are probably not going to lose points in this homework unless in this midterm unless until you don't try. You have to make a bit of effort, and it shouldn't be too hard. If you don't do the basic things that are asked from you, which will be stated very clearly on Monday, then you will lose points. But otherwise, it shouldn't be a very hard homework. Any more questions about the midterm? Okay, good. So let's share my screen. And so last time we introduced the notion of chemical potential, which, as you will see today, is super important for the concept of phase diagrams, which is the next few lectures in this semester. So in order to talk about phase diagrams, we first need to really understand chemical potential, otherwise there is no point. So, and that's why it's important that I recover the material from last time. I would have done it anyway. So let's do that. So the idea was, so this is a recap from last week's class, last class's material. So the recap, the idea was that we care about dg/Tp less than 0. At constant temperature and pressure, this is the direction of spontaneous change. So this is very general. This just says that if change in Gibbs free energy should be negative. The question then is, what is dg? And we know that dg is equal to vdp minus sdt, right? This is integrated first and second law of thermodynamics. We originally stated it for du, but this is equivalent to the integrated first and second law of thermodynamics for du. So similarly for du, we have du is equal to tds minus pdv, and so on. We have relation for dA and dH. But the question here is that in this one, we are assuming that pressure and temperature are the only variables that are being changed. In this one, we are assuming entropy and volume are the only variables that are being changed. Number is being held constant. What happens to the system as you change the number? So to do that, we can write it down mathematically. We can say, well, let's say there are n, capital N number of components in the system. And let's say each component changes by amount dni, small dni, okay? So then there will be a corresponding change in the free energy. That will be partial G by partial Ni, keeping temperature, pressure, and all the other J's, all the other Nj's constant, not equal to I, right? So this is just a definition. Similarly, we can say for this one that this will be I is equal to 1 to N partial U by partial Ni. This time we won't have constant temperature pressure, we will have constant entropy and volume, Nj not equal to I multiplied by Dni. And similarly, we can write down something for dA, we can write down something for dH. You can see last lecture's notes. So if you look at it at first glance, it seems like, well, we have different things, right? Why should this have anything to do with this thing? Turns out they are the same. And we showed this in last notes. Why are they the same? You can start from just the dg formula and then you can derive du. So you can start from dg and we write it down as dg is equal to vdp minus sdt plus I is equal to 1 to n, and we give this thing a name. The name we give it is mu I, the chemical potential of the species I multiplied by dni. From this, you can show that this implies that du is equal to tds minus pdv plus summation I is equal to 1 to n mu I dni. The same mu I shows up here. If you have mu I over here, it's the same thing. Hence, mu I must also be equal to this thing. Partial of u with respect to ni, but now holding s and volume constant. You could do this in the opposite direction also. So these two statements are exactly equivalent. They imply each other. And similarly, we can write down, I will write down the full, I guess I have it in my notes last time. We can similarly write down dH is equal to TdS plus VdP plus summation I mu I dni. And in this case, you can see mu I is equal to partial H by partial Ni, keeping entropy, pressure, and Nj not equal to I constant. And so we have dg, du, and dH we have written, and let's write down a similar one for dA. dA is equal to minus sdt minus pdv. This is something that follows from integrated first and second law. And I will answer your question in a moment, Matt. So plus mu I dni, where mu I is partial A by partial Ni at constant T volume Nj not equal to I. So what Matt Laskowski is asking, why do we use the same mu I for everything? That is exactly the whole point. Let's say you don't. let's say you just start with this one. Okay, let's say you start with the definition for dg. You wrote vdp minus sdt plus mu I dni, where mu I is partial g by partial ni. You can take this definition, you can use g is equal to h minus ts, or g is equal to u plus pv minus ts. And using this, you can write down a relation dg is equal to du plus pdv plus vdp minus tds minus sdt. Once you do that, you will automatically see in one line that du must be tds minus pdv plus summation I is equal to 1 to n mu I dni. And at this point, you realize, hold on, I could have also written my du as tds minus pdv plus partial of u with respect to ni, keeping s volume and j not equal to I constant. That is why it is the same thing. So if you write, it's a subtle point. And if it's not clear, I want you guys to ask me on Slack once again. We wrote G is equal to this. We write down dG is equal to du plus pdv plus this, and you automatically get this formula. I will connect. First you get blue. First you get this one over here. And then you realize that you could have written du in this form, the green one. Second.
I think you're frozen.
Okay, sorry about that. That's why it's good to use colors once in a while so you can see. So the point here is that you write down dg mu I is equal to dA by dni, but you can never say that, never ever say that, because you have not specified dg as to what is being held constant. That's the whole point. Mu I is partial A by partial Ni. If you keep something special constant, it is partial G by partial Ni. If you keep something else constant, it's all about what is being held constant. And this is why multivariable calculus, you always need to have subscripts. If you don't have subscripts, you are going to make a mistake. This is terrible once again. Let's try to do something. Okay, does that answer your question, Matt? It will be cleaner once I share my
I guess I'm still a little confused because you mentioned that we're changing what we hold constant. And that's why we have dA, dN, something held constant. And it's different when you have dG, dN. You have different things held constant. So it seems weird that you're using the same equation. Like I understand that you say like, oh, I see I can algebraically manipulate it and that summation is still there. Yeah. But we're changing what we hold constant for.
That's the beauty, that you get this wonderful relation out of this. That's the beauty. The fact that mu I can be defined from two different things. And it shouldn't be a surprise, because in the end, what is the, let me log in into Zoom here as I speak. In the end, are G and A really different from each other? They are not. All you are saying with G and A is they are all related to the, they are all related to the entropy of the system, total entropy of the system, right? That's where it all comes from. For a constant temperature and pressure process, the total entropy of the system plus surrounding becomes equivalent to talking about the free energy, the Gibbs free energy of the system. And if you do that, you get chemical potential if you're talking about constant temperature and pressure and differentiate Gibbs free energy. If you're talking about constant temperature and volume, differentiate something else. So it's all basically, if you understand that dG and dA essentially follow from the second law of thermodynamics, then that's why they are all similar. This is why it looks so strange, but it's not, because it's all a re-expression. You can think of it, all of it being as S total differentiated with respect to Ni. That's all there is. Now, S total happens to be something else in constant temperature and pressure. That's screen sharing is really being miserable today. Okay, I'm going to pause my recording for a bit, and one of you, okay, recording has resumed. Great. So This is a subtle point, and that's why it's worth our time to spend again some a little bit more of time. I'm not rushed for it. So once again, dg is equal to vdp minus sdt plus summation mu I dni. This directly implies that du is equal to minus TdS This directly implies that du is equal to minus TdS minus PdV plus summation mu I dni. Going from equation 1 to equation 2 is what we call trivial. There is nothing there, right? You just plug in the formula for G and U and H and you get this. But at the same time, you have to recall that du, if you forget about equation 2 completely, you can write down du purely mathematically as du is equal to minus TdS minus PdV plus summation partial u by partial ni, keeping s and v and nj not equal to I constant dni. This is equation 3. Equation 2, and again froze. No, I'm back. Sorry. So equation 2 and equation 3 both are expressions for du. They are both completely valid expressions for du. If you compare 2 is equal to 3, TdS cancel, PdV cancel, and you must have summation I mu I dni is equal to summation I partial u by partial ni at s v nj not equal to I dni for all dni. And this is a trick we use in algebra or calculus all the time, that if such an equation is true with differentials for all possible differentials for all possible variables, the only way that can happen is if mu I is equal to partial u by partial ni at constant s, v, and j and j not equal to I. Okay, that's where it comes from. And I'm happy to go over this again and again because this is an important concept and books really don't go over this in much detail. Okay, and believe it or not, my screen is again frozen. So think over it again, and if not clear, I will maybe record a separate video on this point and do it in even more detail, but I think that's what it is. Okay, so this is one of the things we did last time. What else did we do last time? Last time we also talked about Gibbs-Duhem equation, which was the relation I'm really sorry guys, it's hard enough to take a class at 9 a.m. and it's even worse when the computer keeps freezing. I tried the Ethernet cable, not the Ethernet cable, the USB-C to USB connector, and it was not working, but I'll figure out something. We'll get there. Good. So from this, it follows, and have I resumed recording? Yes, I have. From this, it follows that mu I is equal to partial u by partial ni. And similarly, you could derive relations for mu I is equal to partial a Why is it freezing? Okay. Okay, it's 9:25 and this is, I think, irritating for all of us. I'm going to take a solid 5-minute break and solve this problem and come back. So it's 9:25, we are going to resume at 9:30. Let me figure this out. There has to be a better way. So as a true scientist, I have tried something random. Let's see if it works. If it does, then wonderful. Okay, so similarly, you can derive mu a is equal to partial a by partial ni, but this time you will have to be careful that what you hold constant is temperature and volume and nj not equal to I. So all of these relations are essentially statements of the second law of thermodynamics. They all follow from the second law of thermodynamics. And the variable that is being differentiated changes, the variable that is held being changed, that is held being constant changes, but it is all talking about the change in entropy of the full system. So the other thing we did last time was to talk about the Gibbs-Duhem equation. Gibbs-Duhem equation, I will first write down the equation itself. The Gibbs-Duhem equation says that summation I is equal to 1 to n for an n component system. If you keep the ni constant, and somehow if you change the chemical potential of a species by doing something, then this must be equal to n VdP minus SdT. And if the process is happening at constant pressure and temperature, then this left-hand side must be equal to 0. This equation on its own will come useful later, but in order to derive it, we went through some jugglery, which was quite interesting and important. There we said that G is an extensive function, which means that G, when expressed as a function of N1, N2, and N, the number of species of different things in the system, it can be written as dg is equal to summation I is equal to 1 to n partial g by partial ni, keeping all the other ni's constant. And this is at constant temperature and pressure. So we are talking about g as a function of, is there any way to change chemical potential of I other than a reaction? Typically reaction is the way to change it, but we will see some examples later. Good question, Alex. Chemical potential is like, I was going to get to some more intuition for chemical potential today when we got to phase diagrams. Now it will happen on Monday. But chemical potential, it's called potential for a reason. It's almost like the gravitational potential. How do you change the gravitational potential? Well, you move up and down in height, but you will see parallels when we get to that. So for now, it's, yeah, let's just take chemical reaction is what changes it. Or something else in the environment could change it. Other factors beyond you that you're not considering. Something in the environment causes the chemical potential of I or J to go up. Yeah. So what are the two constants after G? Constant T and P, constant temperature and pressure. So we have dG is equal to partial G by partial Ni not equal to J, dNi. And here we called this as G bar. And also we have constant temperature and pressure here because we are talking about constant temperature and pressure. We call this a G bar. So G bar is defined by partial G by partial Ni, constant temperature and pressure, and J not equal to I. This thing is called the partial molar Gibbs free energy, Gibbs Fe. And notice that this is exactly the same as the definition of chemical potential, right? Because chemical potential is partial G by partial Ni at constant T, P, and J not equal to I. So mu I, and this is, should be G bar I, this is molar volume for I. Mu I is equal to G bar I. Therefore, dG is equal to I is equal to 1 to n mu I dNi. we can write down similar relations for other extensive quantities. We could think of the Helmholtz free energy as A as a function of N1, N2, any extensive quantity. And then we can write down dA. This one's not freezing. So the only thing I changed, so I had assumed that, so you must have experienced it at your homes also. The Wi-Fi has a 3G and a 5G, and I knew that if one is on 3G, the other is on 5G, it doesn't work. So I was always keeping both on 3G. Today I shifted both to 5G and it's not freezing. So fingers crossed, if this works, it will improve our appreciation of thermo way more. So we can write down this one as partial A by partial Ni const. I don't want to do yoga with you. Sorry about that. And this will be again constant temperature and pressure because we are talking about constant temperature and pressure right now, right? Nj not equal to I multiplied by dNi. So why do we have constant temperature and pressure this time? Because we are talking about a constant temperature and process, when temperature and pressure process when we are talking about this. And this is known as A bar or partial molar Helmholtz. And the thing I wanted to emphasize last time is that A bar is not equal to mu I. Why? Because mu I, when it was defined in terms of, this is why you have to be very careful in writing down what is being held constant. When we defined mu I from A, what did we keep constant? Clearly we kept Nj not equal to I, but what were the other two things we kept constant? Anyone remembers?
VNT.
VNT, right? Volume and temperature. And what do we have here? PNT, pressure and temperature. So they are not the same. So G bar is equal to mu I, but A bar is not equal to mu I, H bar not equal to mu I, and things like that, okay? So this was one of the crucial things last time, which is again not written in textbooks very clearly. So let's focus on our G. For G, we wrote down as dG is equal to I is equal to 1 to N G bar D and I, sorry, and these should all have subscript I. We are talking about species I. So this is not freezing at all. It's like my life, quality of life has suddenly changed with this. I imagine for you all too. So I is equal to 1 to N mu I dNi, right? This you can always write down for anything, this part over here. But the part to the right, you can write down only for dG because mu I is equal to Gi bar only for dG. So mu I is intensive, right? So let's write that down separately. dG is equal to summation I is equal to 1 to N mu I dNi, where mu I is intensive. So if we integrate these two things, we can take the mu I part outside the integral because it does not depend on how you are varying Ni, it's intensive. So G is equal to summation I is equal to 1 to N mu I integral dNi, which is, we're going from some 0 to some G, and this one we are going from some 0 to some Ni. So this is I is equal to 1 to N mu I Ni, or G is equal to summation I is equal to 1 to N mu I Ni. Such a relation you cannot write down for A. So I could give you a final exam where I would ask you to say, is this relation true? Prove or disprove. A is equal to mu I Ni. G is equal to mu I Ni. And even though mu I was defined as the same way for A and G, the partials were different. Therefore, this one is not true while this one is true. Once we have this, let's focus on, without loss of generality, just for a two-component system. For two-component, we have dG, or sorry, we have G is equal to mu1 N1 plus mu2 N2. Or in general, we can write down dg is equal to summation mu I dni plus summation ni d mu I, right? Just by differentiating this thing. So once we have this equation, once we compare this with the original formula for dg, what do we have? We also have dg is equal to vdp minus sdt plus summation mu I dni. And just the same idea that we did last time to compare both of these dg's. When we compare this, we see dg is equal to dg, so we can compare them. In mu I dni and mu I dni cancel out, and we are left with summation ni d mu I is equal to vdp minus sdt. So summation ni d mu I is equal to vdp minus sdt. This was our Gibbs-Duhem equation. Summation ni d mu I is equal to vdp minus sdt. So it's as if the gods of physical chemistry wanted me to suffer for not having recorded the video last time and go through the same material again. This is what I did today. And any questions about any of this?
Yeah, I have a question. So at the top of at the top of this page where it says A bar is not equal to mu I, and we're saying that because Helmholtz isn't being measured at its natural variables in that case. But if we're not measuring Helmholtz at its natural variables, can we really say that it's change in Helmholtz?
You can always talk about change in Helmholtz. That's a good question. The reason why you can always talk about change in Helmholtz is because it's a state function, right? And if you recall that Gibbs-Helmholtz equation that we did that related G to change in H, you could perform a process. That's the beauty of all these relationships, okay? You can perform a process holding something constant. Then you can use these relationships to talk about some other state function during that process, even if its natural variables were not held constant. So you can still talk about it. This, on the other hand, is just a mathematical peculiarity or mathematical statement that A bar is held TP and J not equal to I, while mu I comes with V and T. So I don't know if I answered your question.
Yeah, that's fine. Thank you.
Okay. Noel says, why does it change to Ni d mu I at the bottom? Well, Ni d mu I comes from this. G is equal to summation I is equal to 1 to n mu I Ni, right? So I differentiate both these sides. Let me do it in full instead of being like, what's the name of that really miserly guy without hair in Simpsons? Not Homer, his boss. What's Homer's boss name?
Mr. Burns.
Mr. Burns. Let me not be like Mr. Burns and try to save fictional space. I just showed that GI is excellent. I showed GI is equal to this thing, right? So I differentiate both sides and I get I is equal to 1 to n mu I dni plus I is equal to 1 to n ni d mu I. Is that okay? And now we also have dg is equal to vdp minus sdp plus mu I dni. That is how we introduced our mu I. And we compare both of these. When we compare both of these, this mu I dni term cancels out, and all that we are left with is these two. Therefore, summation I is equal to 1 to n ni d mu I is equal to vdp minus sdt. And this is our Gibbs-Duhem equation. And at constant temperature and pressure, this equation also says that I is equal to 1 to n ni d mu I is equal to 0. That's another form of Gibbs-Duhem equation. So there is, yeah, this is DNI. If it looks like a 2, it's not, it's just DNI. Okay, so that's give to him equation. And I'm not going to start the concept of a phase today. I want you to think a bit more on chemical potential, become a bit comfortable with it. And next time we will start with phases and phase diagram. And this chemical potential is, we are going to look at things such as the phase diagram of water, which talks about pressure and temperature, and it looks something like this. You have a solid region that goes like this. You have a liquid and gas region, which goes, solid is over here and gas is over here. This one is called triple point, at which solid, liquid, gas all can exist. This one is called critical point. And we are going to understand over the next few classes as to why is it that this curve, and this is for water, why is it that the phase diagram for water, the solid liquid boundary looks like this? Why does it not look like this, for example? This is wrong, and we will understand all of this. We might also look at some complicated phase diagrams. The most famous one of them is something I had to remember as an undergrad in India. I never did, so I always lost points in exam. This one is a temperature composition phase diagram, where composition is percentage of carbon in iron. This is called the iron carbon phase diagram, which looks something like this. And it goes on and on. It's like random lines being drawn here and there. In one of the midterm papers, you have the phase diagram for relevant to the oceans and ice and salts, some solvent mixed in it. The other papers also have phase diagrams. So we are going to become comfortable with all these things. And the key to understanding these things is chemical potential. We will show an equivalent statement of second law of thermodynamics in terms of chemical potential as how the chemical potential drives whether matter moves from here, solid to liquid, or from liquid to solid, and in general from one phase to another. How does the chemical potential is the driver of this. Just like gravity drives whether you move up or down, if the direction that you take is decided by gravity, or in an electrical circuit, it is directed by the electrical potential, and chemical potential does the same thing for mass. So next time we will start with this. We are also going to study the Gibbs phase rule, which looks something like F is equal to C minus P plus 2. So you can go up and open your Atkins book or any other book and go over phases. That's our next topic from Monday. Sorry about the video problem today, but I think it didn't freeze. So I'm very positive. I don't know about you all, but I feel like there was a clear phase transition in the probability of freezing, of the screen freezing, once I switched both networks to the 5G. And what else did I want to say? There is, you should please look at the papers, take 5 minutes to look at it. You will form an initial impression. If you take 5 minutes to decide which paper to pick, it will simplify your life over the next 3 weeks. So why not do that, right? It's worth it. Take 5 minutes to go over the papers and make your mind. You can take more time. And again, once you come to a team, you are not committed to taking that paper. You can change your mind if you convince your team members to do that. I'm open with that. But please take your time, fill up the poll, and at 2 p.m. I want to look at it. Monday morning, I will release all the full details of the midterm. Okay, so see you all Monday. I will be having office hours on Monday. I will be happy to talk more about anything. On Monday, we begin our adventures of phase diagrams. See you all.